Hello my friends, welcome to our discussion of enthalpy today. We'll be looking at what enthalpy is and how we measure enthalpy in the lab. Let's get started. So enthalpy basically is the heat either given off or absorbed by a reaction, and that's true at constant pressure. But the nice thing is with chemistry labs, almost always the pressure is constant. Doesn't matter what pressure it is, as long as it stays constant throughout the reaction. And since we do most of our reactions in open beakers and flasks and these sorts of things, we have this constant pressure situation. So basically the word enthalpy, the change in technically the change in enthalpy is equal to the heat evolved during a process. And this letter Q right here is the heat. So when Q is negative, so you have a negative Q, that means the reaction is turning chemical potential energy from the bonds into thermal energy, which is then given off as heat, the heat of the surroundings. If Q here is positive, then that means it is turning the kinetic energy, also known as thermal energy, of the particles into chemical potential energy, so that bond energy we talked about earlier. So those are the two possibilities of Q. Q negative, and this would be exothermic, so you would feel it getting hot. This is endothermic, because it would suddenly lose a bunch of thermal energy as it converted into chemical potential energy, and then you would feel it as being cold. Awesome. So that's enthalpy. Basically, enthalpy, just think of enthalpy as how much heat is absorbed and given off. And I should be saying here change in enthalpy. I apologize. Change in enthalpy is just that. Now this constant pressure thing really isn't a problem, because almost all of our reactions in chemistry happen in an open container, some kind of beaker or a flask or something. So the pressures are constant. It doesn't matter what the pressure is as long as it's constant. This works. If the pressure isn't constant, then this enthalpy thing, it's hard to interpret what it means, and we won't be working with it. So if the pressure is changing, we would work with something other than enthalpy. Enthalpy is not helpful with changes in pressure going on. Awesome. So just worry about delta H, the enthalpy of the change in enthalpy of a system is equal to the heat either gained or lost by the system. So because enthalpy has to do with how much heat is flowing, we measure it using a calorimeter. Just like we measure the heat flowing out of a piece of metal into the water to measure the specific heat of the metal, we do the same. We use calorimetry for enthalpy as well. So basically, you take measured amounts of your reactants, you put them together in a calorimeter and allow them to react, and then you measure how much hotter the calorimeter gets or how much cooler it gets, and that allows you to calculate how much heat was either given off or absorbed by the reaction. So it's very similar to the last stuff we were doing, calorimetry. Now when measuring the enthalpy in solutions, we're going to make the assumptions here that the solutions have the same heat, specific heat as water does, 4.18 joules per gram degree Celsius. That is not exactly true, but it's a good approximation for dilute solutions. And we'll also assume they have the same density, so that 75 milliliters of a 0.1 molar sodium chloride solution is still about 1 gram per milliliter of density. Again, that's not true, but we're going to make that assumption to make the work a little bit easier. Now you obviously could go back and do a bunch of work to measure the exact specific heat of, say, that sodium chloride solution. It would be a little bit different. You could measure that. And you could also go and measure the density of that solution and use those two numbers. But for our problems, we're going to just assume they're the same. Makes life easier. Then we're going to measure the change in temperature of the solution. So we'll put the things together, we'll let them heat up in the solution, and we'll know how much the water heated up by, and then using the specific heat of water, the mass of water in the calorimeter, and its heat change, we'll be able to find, or temperature change, we'll be able to find how much heat was absorbed or lost. And then finally, when we're doing delta H stuff, we typically report our values in kilojoules per mole. So that'll be important later on. We'll get to that. So let's get a real example. So here's what would happen. So Hannah has 75 mils of a 0.4 molar nitric acid solution, right? So it's mostly water with a little bit of nitric acid in it. And she mixes with that 50 mils of 0.6 molar solution of sodium hydroxide. Again, mostly water, some sodium hydroxide. Both solutions start at this temperature, 22.65 degrees. And then the temperature when she pours them together jumps up to 25.84 degrees. And we're wondering what the change in enthalpy is of that reaction. So basically, how much heat was generated by that reaction. And we can see that the Q for this reaction is actually going to be negative because the water heated up. So the Q for the water will be positive because it gained energy. And then the Q for the reaction is going to have to actually be negative because it lost energy and gave it up to the water. So let's do this and see what happens. First thing I notice is there's no balanced equation. So this is a reaction, so I'm going to balance equation real quick. And I'm actually going to put it up here because I'm going to run out of room down here, I think. So we have nitric acid, that's HNO3, and that's aqueous. Plus, we have our good friend sodium hydroxide, NaOH, and that is also aqueous. So we can come over here and we can say, okay, so what really happens here is we get H2O, that's a liquid, plus NaNO3, and that is also aqueous. So that's our balanced chemical equation right there. So it looks like, yeah, totally balanced. So everything's great. So it looks like we have to come down here and figure out what things we know and don't know now. And one thing I noticed first of all is I'm given an amount of both the sodium hydroxide and the nitric acid. And I don't know which of these is going to run out first. Whenever you're giving volumes of two of your reactants or amounts of two of your reactants, you need to figure out if one of them is a limiting reactant or not. So let's do that right now. The reason we have to do this is if one of these runs out first, that's the one we have to use in the problem. We can't use the one that has excess of it. So hopefully in this problem they're going to run out together, but we have to figure it out first. So I know I need 1 mole of nitric acid for every 1 mole of sodium hydroxide. So if I figure out how many moles of nitric acid I need to have the same number of moles of sodium hydroxide. To do that, I know that the number of moles in is equal to the molarity times the volume. So my number of moles of nitric acid is going to be 0.0750 liters times the molarity of 0.400 molar. And that gives me a number of moles equal to 0.0300 moles HNO3. So I'll have to compare that. I know I need, for every 1 mole of these, I need 1 mole of sodium hydroxide. So I need 0.03 moles of sodium hydroxide. So I'll do the same thing here. N is equal to the molarity times the volume. N is equal to, but now I'm going to use sodium hydroxide. So I'm going to say 0.0500 liters times 0.600 molar sodium hydroxide. And that gives me the number of moles of 0.300 moles NaOH. And sure enough, I'm super lucky that they work out to be perfectly matched for each other. They are both limiting reactants, which what that tells me is I can use either of these number of moles I want to use in the problem. All right, awesome. So we've established limiting reactant. They're both limiting. And now we need to figure out what we're really looking for. And we're looking here for the enthalpy, and that's the amount of heat that's given off. And I should say here always the change in enthalpy. That's the amount of heat given off by the reaction or absorbed by the reaction. In this case, the water heated up, so it was given off by the reaction. So to figure that out, all I can do is figure out how much heat the water absorbed. So here I'm going to say this is the heat H2O absorbed. And to do that, I'm going to use this Q equation. Q equals MC delta T. And this is all for water, right? So I'm going to use all water information in here. So the Q is equal to the mass of the water, which is the 75 milliliters plus the 50 milliliters. All right, we're going to assume that this is just basically all water with a little bit of this other stuff in it. 125.0 grams. We're going to also assume a density of 1 gram per milliliter. Again, those aren't perfectly accurate assumptions. You go back and measure the densities of these two liquids and find out the actual masses of the water inside them, which would make it super tricky to do. And then, so C is 4.184 grams per degree Celsius. Sorry, joules per gram degree Celsius. I got sidetracked, so my brain was thinking about something. And then times the change in temperature here, which is 25.84 degrees Celsius minus 22.65 degrees Celsius. And when you do all this math, you get a Q equal to 1,667 joules. Awesome. So that is the amount of heat the water absorbs here. So this is the Q for the water. Now, of course, if this is the Q for the water, the Q for the reaction is going to be equal but opposite sign. Because if the water gained, the Q here was lost. So negative 1,667 joules for the reaction. And we know here that the Q for the reaction is equal to delta H. So for this exact reaction with this molarity and this volume, that's how much energy is produced. But the question is asking us to do also the molar enthalpy change. So what is the enthalpy change per mole of stuff? So in this case, the number of moles of nitric acid and sodium hydroxide are the same. So we can use one of these two, not both together, just one of them. And we'll quote it as being so many kilojoules per mole of that stuff. I'll show you how to do that in a second. So to do this, though, we want to do this many mole, this heat. So we get negative 1,667 joules. And in the end, we want joules per mole. So that means we just divide by the number of moles. And we can, again, use either of these because they're the same. 0.0300 moles. And that gives me a delta H of 55,600 joules per mole. We can also write this as 55.6 kilojoules per mole. Sorry, the writing's getting sloppy. The pen's a little falling behind on me here. So this is my delta H of the reaction, delta H. Now, no difference between a delta H of a reaction and one that's a molar delta H. You have to look at the units here. This is kilojoules per mole, and this one is just joules or kilojoules here. All right. So that gets us down to it. So if we had for every mole of reactant we have, we produce 55.6 thousand joules. And notice we only had 1,600 joules here because we didn't have a full mole. We only had 0.03 moles of stuff. So that is our final answer, as well as this one. All right, so that's how to do those kind of problems. We'll do these in the lab and get some more practice at them. Have a great day, my friends.